Hello, everybody. Yeah, welcome to our Tuesday session of the ARIVE XR lecture series. Good to see a good turnout here, both in this room here as well as in cyberspace. Today's speaker is TJ from the Victoria University of Wellington, and he will talk more about the photorealistic side of XR, and I'm really looking forward to that. And I hand over to TJ. Thank you very much.
Okay, thank you, Helga. I will share a screen.
Yeah, we can see your screen. All good.
Okay, great. Okay, I'm Taehyun James Rhee. As Holger said, simply call me TJ. Audio is fine. The video is fine. All good. Yep. I'm a director of Computational Media Innovation Center, we shortly call it CIMIC, at Victoria University of Wellington. First, I share my special thanks to Holger and Tobias, who initiate and organize this ARIVE lecture series, and also Mark, who initiate the ARIVE consortium. And it's my great pleasure to share my talk online with audience from New Zealand and Australia. Is anyone from outside of Australia and New Zealand today? I will share a special thank to you. Today's title is Photorealistic XR Part 1, but actually it was a tentative name suggested by Holger and Tobias, but I feel like it's a cool name, so I keep it, and that is quite fit to our my talk today. We prepared the two talks for this topic in this week. The part 1 is the thing that I will cover today, including some background story about our center and the digital media ecosystem and photorealistic rendering and composition and human visual system and photorealistic mixed reality, and also high fidelity telecollaboration and telepresence. Okay, have you seen this valued sign in Wellington before? Anybody else? Actually, this is a CG. So I thought it's a real, but it's a CG. And this is related to our today's talk. As you know, that New Zealand is well known for CG-like beautiful real nature. So the picture here is actually the photo, not CG. And we contributed many movies and commercials. Some people may know that the famous directors such as Peter Jackson and James Cameron live in Wellington and nearby. And Wellington is has a strong entertainment sector and also digital media sector. And we have like a Oscar-winning visual effect company, Weta Digital and Weta Workshop. And this is a table that I list a top 10 highest grossing film in the global market. As I'm aware that we have 5 out of 10 film contribute from Wellington and this country. To support the strong media and the entertainment sector of this country and the city, our university initiated a postgraduate program for computer graphics in collaboration with Weta at 2012. And I joined their first full-time, as their first full-time academic step to build the program from the scratch. We opened the computer graphics lab in 2014 and made a new undergrad program at 2016. And initiate a mixed reality startup, Dreamflug, at 2017, and started CIMIC from 2018. After 8 years of hard work of our team, our university, I believe that we made one of the largest computer graphics academic group in Oceania and built a pipeline to link academic research to industry. Actually, before joining Victoria in 2012, I worked at Samsung for 17 years. So I was a principal researcher and the senior manager to lead their computer graphics and mixed reality research at Future IT Center and work with the CTO to build the technical roadmap for their 5 and 10 years of research direction. And recently we opened a new center called Computational Media Innovation Center and opened a new office last year and to strengthen expanding our potential to work with overseas collaboration. So CIMIC is literally at the center of Wellington City. And as I mentioned, that we built a new office in 2019 with lots of cafe and bar nearby. And we have brand new state-of-art research facility and the equipment to support future digital media research like VR, XR, and MR. We have 25 researchers, including 15 staff and 10 students, and then rapidly growing. We have three groups in different expertise. First group is a computational media solution group. We call it CMS. It developed technical solution and IP to innovate digital media platform. We cover computer graphics, computer vision, and machine learning, and audio and video processing. And UXR, user experience and XR group, design and evaluate new user experience for future media service. They cover XR area and also UI and the user experience. And advanced media prototyping group, we call it AMP, covers um, um, prototyping for the advanced media application to foster new media business. So three groups work tightly together to solve complex interdisciplinary problem and collaborate our industry partner to foster future digital media business. DreamFlux is one of our flagship projects at CIMIC to commercialize our XR research. We actually recently launched a startup company in US called MR360 Light Lab. Can I mention about the future digital media? So what is the future digital media? We need to start with the current digital media. So I picked the two famous digital media sector, movie and game. Let's see the ecosystem behind. So people are watching movie, but to experience a movie and have a watching experience, we need to see the film produced by movie studio. So in this case, the experience is watching and the media probably film. When watching film, we experience a new story for fun and empathy, and we spend lots of money for this kind of value. And the game industry, so we experienced some play and entertainment that is made by the game studio through the game. And actually, the thing that we can earn from the game is entertainment and fun, and the value of the fun experience is also significant. And one of the hidden layer in this ecosystem is the hardware and software platform to watch and play. We need to have a display and the interface. The revenue of a consumer electronics market is huge. I was in this like a platform business in my industry experience, and I also working in the university together with a content provider in the game studio and a movie studio. In the movie industry, the user experience are advanced toward more fidelity and immersion and interaction toward the presence and the story. And as you know that the VR provide a solution for presence and interaction for immersive experience. It is an ideal tool for immersive experience for training, prototyping, education, and planning. However, due to the high cost of the VR system, it has been limited by B2B business to business business for special users until 2015. But in 2015, the VR ecosystem has been changed after Oculus produced a consumer level VR headset. Many companies released VR equipment to consumer market. So it motivated innovation of the conventional digital media sector, such as a movie and game, into immersive media market. So movie studio provides 360-degree films, and game developer provides software for VR headset. With consumer available VR headset, people can experience VR at home to watch and play and simulate the VR contents. So it opened a new emerging market, and this is a significant improvement. And in my point of view, there's some more we can do in this sector, so film. So the current movie ecosystem based on 360 film has a limitation for interaction that constrain full immersive experience, which is beauty of the VR. So this is an example of VR with 360 video. So this is a common setup using the immersive film at VR in the film industry, which is great to provide wide field of regard and then telepresence at the capture location, but has no interaction except 3-degree freedom head rotation. So recent research provides a partial 6-degree freedom movement, but has no actual interaction with the object in the scene. This is what we do. Our MR360 solution made by CIMIC and DreamFlux team provide high fidelity mixed reality, which can blend dynamic 3D object into 360 video in real time. Based on the consistency of lighting and shadowing and realistic rendering and seamless composition, it provides illusion to play with object in the 360 video with high telepresence at the captured real space. And the quality of lighting and blending has been a major factor of visual effect movie. This is a part of the behind movie scene of Hobbit from the FX guide. In this scene, we have an actor and a 3D troll, and the actor is in the studio set, and the troll is in the digital world as a 3D virtual object. How about this? After proper lighting and the blending, they are now presented in the Mirror Earth. If we fully immerse in the movie story, we also feel telepresent in the Middle Earth. Now, this kind of concept of presence and high fidelity mixed reality rendering has been applied in the visual effect pipeline for various movies. So the movie studios such as Vera Digital has built an ideal pipeline to seamlessly blend 3D virtual object into captured film. It allows high sense of presence in the movie. However, the pipeline rely on the manual blending and offline computation for creating the final outcome. And on the other hand, augmented reality games such as Pokemon Go provide online and automatic blending, but the quality of blending and the presence in the scene is low compared with the movie. And then, so our aim is to provide a solution to interactive application for immersive presence. So like online and automatic blending. And if we provide the solution successfully, it can converge VR and AR and the pipeline of the game and movie in a unified platform. So there are many challenging technical challenges, huge. Compared with the movie industry, we need to have millions time faster rendering and then outcome. We also need intelligent algorithm for automatic pipeline, and also we need a convenient user interface. This is one of our student project of my rendering course. The aim is to make the seamless blending between the virtual and real object using PBRT, physically based rendering tool. This is offline rendering tool supported by the physically accurate rendering outcome that is based of the WebTAS pipeline. And this is mixture of virtual object and the film, the photo. So can you recognize which one is a virtual, which one is real? So I played the video, the moving object is virtual, the other is real. Okay, there are several technical challenges for making realistic rendering and composition even in offline setup. In film, we use algorithm called ray tracing or path tracing. The algorithm is based on the light transport simulation to mimic light penetration in 3D scene. In this case, we open shoot 100,000 sample ray per pixel, and each intersection point, we compute the color, and that is based on this kind of rendering equation. So the F is material property, L is lighting, and G is a geometrical term. And the final result is a kind of a color of the intersection point. And in the particularly for mixed reality and then like a visual effect company like Weta, we need to use the light from the real world. So we need a technique called the image-based lighting for creating the realistic lighting from the real world background. And also the final rendering need to be blended with the real world footage. In film, the composition has been done by manual work by artists using some tool like a Nuke and After Effects. But the mixed reality and augmented reality, we should do it automatically using the differential rendering. So this is one of our previous work to contribute to save rendering time of red tracing. In this scene, we shoot 1,000 samples per pixel. Rendering time is a couple of hours per single image. One of the common solutions is to shoot a limited sample per pixel, then use denoising technique while considering the outcome as a noisy rendering. But we address this problem in different way. We shoot the full sample per pixel, but render only a limited pixel, in this case, a 20% of pixel, and then tackle this problem as the image completion problem to recover the missing pixel better than denoising. So left part is like input, and the right part is our recovery. So we recovered the limited sample image, like 20% and 40% pixel. Then we recovered the final rendering, which is exactly similar to the reference. So what's the behind technique? So I do not want to go deeply about the mathematics behind. And it's like that the input is just 20% of pixel. The first step is to use convolutional neural network to fill the missing pixel using the trained network roughly. And then we use some method called the matrix completion, find the similar patch and then make a low rank matrix, and then solve the nuclear norm minimization to fill the missing element. So if you are interested for the more math and then behind, then you can refer to the paper. And the result is quite like better than our expectations. So as you can see, only with the 20% and 40% pixel, we recovered almost the perfect final outcome using the combination of the machine learning and the matrix completion. But this is a part of the way that we can save the time of the final rendering. And as I mentioned that the image-based lighting is important to use the real-world light. This is an example of the scene of the movie. As you can see, the top right, that's like a equivalent format of the light map or called the radiance map. We capture the surrounding environment, the light source, and use it for the real-world lighting and render the virtual object. So this is another project that we did with the Weta. So the company like Weta has more than 10,000 light map, which can be used for the backdrop and the lighting. In the actual practice, the backdrop of the scene is often requested to be changed. And instead of go out and capture another sky image, we can search the database to change the sky image. But how we can search? So that's kind of question. So we try to find the semantic feature to describe the sky and then make a sky browser for artists to search the images. The work has been published in the Pacific Graphics and also used for the visual effects pipeline at Weta. And the detail will be covered by tomorrow's talk. Recently, we built a way to browse a light map using the illumination component rather than the texture component, like a sky browser. It allows studio artists to find the proper lighting for visual effect and also high quality mixed reality use case. Okay, so so far, we checked a few methods to address realistic rendering and lighting, but this is based on the offline. So the remaining challenge for high fidelity immersive interactive XR is first, we need to solve the problem in real time. The global illumination and image-based lighting and different rendering should be done in real time, especially for application of a VR headset. We need more than 90 frames per second, but for the stereo, we need like a 180 frames per second rendering to mitigate the visual discomfort. This is quite over the general setup for gaming environment. So sometimes mostly use a 60 frames per second. And also we want to use a usable solution without any pre-computation for adapting live streaming video and support IVL image-based lighting with a conventional low dynamic range image rather than high dynamic range image. Finally, we wanted to keep the visual quality as high as possible. So there are many challenges here. So how we can do it? This is the thing that we address that problem. So the ultimate receiver of the final image is a human eye. So our receiver is our eye. So if we can provide a final output that human eye perceive it is realistic, I think it is enough. So we often overshoot our resources and computation beyond the scope of a human visual system. And then we wanted to meet our resource and computation exactly meet the human visual system. So this category of research is called perceptually based computer graphics. So metric to judge the visual quality for seamlessness and presence is that impression of the synthetic object belong and blended in the real world scene or belief or presence of the synthetic object in the real world surroundings. For example, in this scene in the avatar, we feel the avatar is in the laboratory with the scientist, the same environment. So we did a couple of perceptual study, and then this is one of the example. Based on the series of a perceptual study, we observed that although we reduced the size of the light map, people could not perceive abnormality in the final rendering. So the visual effect company, they can have a 3000 by 2000, 5000 by 3000 light map, but we reduced the size like a 160 by 80, but the final result of the rendering using the reduced size of light map is not noticeable in human eye. So this is actually more than 90% of saving of light map compared with the typical visual effects studio setup. But you probably not believe me, but let's do the actual experiment here. This image is mixture of virtual and real photo. This has been rendered by high dynamic range light map. Resolution is 5000 by 2000. Okay. This is second image. I changed the image, the same setup, but the resolution is 300 by 100. The third setup, this is actually low dynamic range image, just 8-bit, rather than high dynamic range having the 24 and 32-bit. But we converted it as a simple algorithm, and also the resolution is a 300 by 100. Let's see the side by side. The virtual object here is a green block and blue ball. And the result, the left side is the ground truth with the high resolution light map. The rightmost image is the tone mapped low dynamic range image with 300 by 100 resolution. So compared with the original setup, is a 99% reduction. But there's some difference here, but the result of composition of the right image is quite realistic. Hope you to agree that. So we use this finding for solving the lighting and rendering problem for interactive, immersive mixed reality application. And fortunately, from the around 2014, 15, we can have many 360 panoramic video capturing devices. And now we can have a couple of devices can have a live streaming as well. The idea is simple. Use 360 video as a real-world lighting source and also backdrop to light and blend the three virtual objects. And unfortunately, high dynamic range 360 video capturing devices still not common. So the first step is to convert conventional low dynamic range 360 video to high dynamic range format using inverse tone mapping algorithm. But the algorithm itself is just simple equation. It's very, very simple. And then we used our perception threshold to improve the speed of the rendering. The first part is diffuse reflection. The thing that I wanted to mention here is the fact that material and the light are reciprocal illumination. What that means is that instead of altering material property, if we adjust the lighting, we may have a similar effect in final illumination. So for example, just imagine that there is a white ball, but we have a strong red light. And then we can feel that the ball is red. So in order to express nice diffuse material, we used diffuse light map rather than diffuse component of the reflectance. As shown in our previous perception test, low resolution light map was enough to light the diffusion material property. So in the rightmost image is final rendering. So for the right bottom, so we use 64 by 32, the very, very tiny light map to render the diffuse object. It reduces resources and also computing time. But the final result remains the same as shown in the figure on the right top. And specular component. So one of the most expensive component of the rendering is to present a glossy specular reflection. Since we need a large number of samples toward the glossy lobe, and that glossy lobe changes when we alter the viewpoint. So in order to address the challenge, we adapt our perceptual threshold as well in the it's like we did in the FTP object rendering. So we use MinMap. MinMap is a multi-resolution image to provide texture anti-aliasing. We use the MinMap for glossy specular reflection. The idea is simple. For a low roughness, we select higher resolution MinMap for sharp reflection. The leftmost image, shiny teapot with high resolution MinMap. And for higher roughness, we select low resolution MinMap for blurry reflection. The rightmost image, like a brushed metal, look like a brushed metal. And then we use the low resolution MinMap. So a final outcome is realistic image-based lighting that we can produce more than 500 frames per second, and then we can cover our various roughness level and with a different lighting setup. So we also implement our image-based lighting into game engine like Unreal Engine 4 and Unity. So it shows a good result. But the illumination using real-world light with real-time image-based lighting is good, but the limitation is to cast a realistic shadow. So we need another step to deal with the shadow itself. First part is to detect the most salient light from the light map using threshold. Then the detected light are converted as a directional light to cast shadow. And especially the larger area of the detected light cause more soft edge of the shadow. So we can change the softness of the shadow based on the area of the light. The final step is to blend the effect into the final rendering. So this is called the differential rendering. So first we compute the illumination difference between the background and the virtual object rendering, such as the shadow and color breeding that is shown in the image E. Then add the rendering of the virtual object and this difference image into the final background as shown in the image F. Then we can have a final outcome. So this is an example of integration in the Unreal Engine 4. As you can see, the lighting and shadowing are automatically adjusted by the altered 360 video. And the artist can easily drag and drop the 3D asset into the 360 video for making their own mixed reality content. This is an example of our 360 live demo. So we can create a mixed reality aquarium, the playground. This is the Wellington Civic Square, and we can virtually visit there, probably from home, and play with the fish. So we show the fish, so we have a special version for the underwater. So we call it MR360 underwater. It provides additional visual effect to create realistic underwater mixed reality experience. So we add the 4 effects. First effect is the underwater caustics. And the God rays for more dramatic effect. And fog. Sorry. And finally, some particles. So for evaluation, we tested 3 lighting conditions: ambient light on the left, and lighting using conventional MR360 in the middle, and then MR360 underwater with the 4 visual effect. And also we tested with and without interaction. So for interaction, we have a virtual hand and touch the fish, pick the fish, and we also feed some food, and they can come to us. And the fish has some AI to follow the food. Okay, so there's some sound, but that's not from my video. I thought it's from video or not. So anyway, so our study showed that the average overall image quality and presence improved when using proper visual effect. And also we found that if we have interaction, people feel higher visual quality and presence compared with no interaction. And this is one of the use case for actual demos. Our DreamFlux and MR360 technology has been applied for the virtual tour demo at Wellington Airport. The project was in collaboration with Wellington International Airport and Wessler, a local production company. And as you can see, there's a tri-show in the airport. People can sit on the tri-show with a VR headset and the controller, and then they can virtually travel to the destination of a Singapore airline and experience the local culture in mixed reality. So the original installation is supposed to be a few weeks, but it was popular, so we extended for a 3-month public demo. But the good thing that I can mention is that there was no technical fault at all. So, it was quite reliable at that time. We also presented our work and some use case in the SIGGRAPH 2018 and real-time live event. We performed a live demo in front of 2,000 audience, but it was a quite good experience. And I can show some video clip of our team's demo today. Can you hear the voice?
Thanks, Lohit. So we didn't bring a booth this year at SIGGRAPH. So I thought it would be really fun to design a virtual booth in real time just for real-time live. So how are we going to do this? So I'm over here physically on stage, but our booth is being set up right over there by Lohit and Steven, my colleagues. And so what we've done is that we've set up a Samsung 360 round camera in the middle of the booth, and that's streaming to this PC over here and into my headset. And that's going to allow me to teleport over there and see what my colleagues are up to and see if I can help them out. So what I'm going to do is, can we switch to my computer, please? Thank you. So I'm going to put on my headset now. All right, so this is where we left off. And I'm going to teleport over to the virtual booth. Oops, wrong one. Give me a moment.
It was a 7-minute live demo, so quite intense.
Awesome. So you can see that it's as though I'm in the virtual booth with Steven and Lohit. So looking at the booth right now, it's a little bit empty. So what I'm going to do is add a few objects to kind of add to my video. So we're going to have a table, we're going to have a chair, we're going to have a little real-time live object.
This is live, and then as you can see, the video quality is quite
also
convincing.
We need a banner, and special thanks to our sponsors, Samsung and NVIDIA, for helping us out. So you can see that it doesn't look too bad. With our lighting solution, we're able to naturally blend digital objects into the video. And so as a designer, it's really easy for me to more accurately pre-visualize what I'm trying to do, as well as keeping immersed in my task. So obviously, this is a virtual booth, so we don't have to stick to regular objects. What we can also do is add something more interesting. So we've traveled all the way here from New Zealand, so it would be a shame if we didn't bring some New Zealand flair over here. So I'm going to add a couple of, ferns to the scene.
Yeah, this is the kind of beauty of like a virtual asset.
Got a
so
log.
we can add some like thing that is not possible.
And of course, we need a booth mascot. So here's a kiwi bird.
Kiwi to Vancouver.
Awesome.
So we can do it virtually.
Okay. So basic layout is done. I'm quite happy. Show an example of this. Show an example of this.
Okay. So next part that I wanted to do is how to use this kind of a technique for remote collaboration. So this is a recent work that we presented in the ARIVE VR this year. So the short name is AVT, Augmented Virtual Teleportation. AVT is a symmetric framework combine VR and AR into mixed reality space to support immersive remote collaboration in XR in high fidelity setup. So far, the thing that I explained with the MR360, we did not consider any person in the teleported space, and this is similar like a planet without no living creature. But we live with other people, so we need a communication, and we also need a collaboration when we teleport it to other place. So in real world situation, in order to collaborate with the person, we need to be in the collaboration side, the work side, and often we need actual traveler, but VR, we can have a virtually travel to the collaboration side. We define the people at the collaboration side as the host, a local host, and the people in the other side who need to travel as a remote traveler. This is one of the example scenario. So let's assume that it often happens. So one of the pipe in Wellington is broken. We need immediate help from the engineer in Sydney to fix the problem on site. Collaborators need to be in the same space, and then to solve the problem together. Engineer in the Sydney need clear situational awareness of the work site, and also they need to communicate face to face and work together to solve the problem. So the normal situation, we just take a flight and come from the Sydney to Wellington, but this is often not possible. This is more obvious at this global pandemic and border restriction. So alternative solution of that our community can provide is field there. In order to go there, we can feel there and aware there and immersive technology. So one of the good examples of Zoom is an okay solution to gather online and then communicate to each other, but the current video conferencing has limitation to fill in on site, to have a full situation awareness of the surroundings to solve the problem in the work site. So VR also tackled that telecollaboration, and it's great. We have a good presence in the virtual space to collaborate, but the collaboration is limited in the virtual digital space. And AR telecollaboration, such as holoportation by Microsoft, is awesome. We can communicate with the remote collaborator through their 3D avatar and augmented virtual object. We can work together, but collaboration is limited by the own local space, and telepresence and situational awareness of the remote site is limited. So our solution is combine VR and AR and then take the essence of VR and AR for solving the problem. Instead of traveling, the remote engineer can stay in their physical space safely, but have a full situational awareness in the work site through live streaming 360 video shown in his VR headset. The local host at the work site, this guy is an AR. So they wear the AR goggle, then communicate face-to-face with the 3D avatar of remote engineer overlaid into 360 camera. And then they collaborate together in the high fidelity mixed reality collaboration space to solve the problem in live. And this is a mixture of VR and AR and mixed reality collaboration space. So as I mentioned, that this is a symmetric setup that converts VR and AR into live mixed reality collaboration. So as I mentioned, that the remote traveler is in VR and local host in AR, they work together in mixed reality space. So the implementation is based on 360 live streaming camera, and we implement for AR side and VR side and align together for synchronization of the collaboration. But the detail of the implementation I will skip it, and it will be covered by our paper. But I will show some captured video of our current ABT for remote collaboration. This video has been made by our team recently and shared with Tech Week demo. The AR host at the work site set up 360 video camera to capture the live stream the space. And then he wears a see-through AR display. But this video, we use the camera attached HMD for better visual quality, but it can be switched to HoloLens and Magicleap. Remote traveler wears a VR headset for immersive viewing and telepresence at the work site. And the VR traveler and AR host will meet in the collaboration site and work together. The left side is a VR view from the traveler, and right side is the AR view of the host. The VR traveler see the local host through the captured 360 video. So, and therefore no avatar is required on the left side. But AR host in the right side, see the 3D avatar is a yellow guy of the remote traveler, and then they can have a face-to-face communication with the verbal cue and position cue and gaze cue. And they collaborate in live mixed reality collaborative space with augmented 3D virtual object here, fun and some dragon. And we make some virtual suitcase that can bring the digital asset from here and there to have collaborate to have a collaboration work. So this is not a concept video. This is an actually captured video from VR view and AR view. And if you can travel to Wellington, we can showcase live demo. And also if we are ready for the internet version of it, we can remotely experience it. And so our AMP group made a concept video for AVT to showcase one of the possible scenario for industry. I hope you to enjoy it. So this is a concept video, not a capture video.
Imagine being able to appear next to someone the moment they need help. A business's success is driven by the skills and actions of its employees. But to work effectively, they need to be able to communicate easily and accurately. Some problems require complex hands-on problem solving and are ill-suited for video calls. When employees face a difficult problem, they need to be able to ask for help, even if those people aren't nearby. That's why we created AVT. Now you can really be where you are needed. Move around with total independence, view from any angle you want, and use augmented reality tools for maximum effectiveness. Using virtual teleportation, you can contribute to solving problems as if you were really there. Upgrade the way your team collaborates and allow them to work at their full potential.
I hope you enjoyed it. So, okay, this is what I prepared today. And so I covered the Photorealistic XR part 1, the left box. And then on this coming Thursday, we will cover the part 2. Today I cover shortly about our background and then some ecosystem that we are interested in, and then some equations and then mathematics behind the photorealistic rendering and composition, and some perception for human visual system, and also the technique that we can leverage from our perceptual finding to speed up the rendering process, the composition process for making interactive photorealistic mixed reality. And then finally, showcase some kind of example of using this technology for high fidelity XR collaboration. This Thursday, 2 days later, the part 2 of the subject will be continued. We will cover the image-based lighting and illumination in more depth, and we introduce our recent paper, which is machine learning technique, especially like a deep neural network and convolutional neural network, to address problem for estimating information for photorealistic XR. I think the method is helpful to extend the photorealistic XR platform to mobile application. So it will be given by Andrew. So Andrew is here, and then Juno from CIMIC. Hope you enjoy this talk, and then hope to see you all again on Thursday. And also you can bring your friends and family. And thank you so much. And then finally, I wanted to introduce some conference that we are hosting. So we host Pacific Graphics, and not only 2020, but also 2021 at Wellington. This is the first major computer graphics conference in New Zealand. Actually, we planned to host the Pacific Graphics in 2020 at Te Papa. We booked it, and it's supposed to be happen next month, but it's not possible due to COVID-19. So instead, we decided to converge 2 years conference, and we'll have a bigger physical gathering at Te Papa next year. Hope to have a physical gathering next year. So if you missed the chance for Pacific Graphics this year, no worry, you have one more chance next year.
Okay, thank you very much, DJ.